Okay, 9.7 probability. We've spent last week finding the number of outcomes. Now we're going to find probability. Probability is a percent. Yes? How? Well, they can be a percent. They can be a decimal. They can be a fraction. Okay, those are all probabilities. But how do you find a percentage? How do you find a percentage on a test?
Like
the number you got
out of overall how many you could have got.
divided by how many you could have got. It's the same thing with probability. It's the number of things you're looking for out of the total number of outcomes. And we've talked about outcomes before. And we're going to keep talking about them. Okay, so an experiment is any happening for which the result is uncertain. Outcomes, if you don't know these, you could write them down, but I would assume you know them per se. Outcomes are the possible results of an experiment. Sample space is the set of all possible outcomes of this experiment. And an event is a sub-collection of the sample space. So we look for an event out of a sample space outcome. Sample space and outcome, kind of the same thing. Okay. You need to know, if I ask you what is the sample space or what are the possible outcomes, you need to know what that is. Okay? Possible outcome sample space is what could happen. Yes? When I roll a dice, what is my sample space?
1 to 6.
1 through 6. When I pick a card out of a deck, what is my sample space? 1 out of 52. Actually, no, sorry. The sample space is ace through king of clubs, spades, hearts, diamonds. That is the sample space, yes? But if I ask you for face cards, that is the event I'm looking for is face cards. See the difference of that now?
Yeah.
The sample space are every card. The event is what I was looking for. I said face cards. Our test is Thursday. Because Friday we're going to do a geometry review for Trig before we get started.
What have we done so far this year that make you think it's
know.
Trig?
I don't know what Trig is.
Well, that's fair, I guess.
Oops. Trigonometry is the study of triangles.
I mean, we are using Pascal's triangle, so technically we are using trigonometry.
Think again, Isaiah.
Okay, am I good?
Yeah.
Elena, are you good?
Yeah.
Okay. Okay, find the sample space for each of the following. Tossing a coin.
1, 2.
Heads and tails. Head,
Yeah, that's basically
tails. Okay.
Heads, tails.
What is the sample space for tossing 2?
2 heads, 2 tails.
Heads, tails.
I can have heads, 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 tails, tails, heads, or tails, tails. I'm sorry, I moved through them like that. Do you have to write them in that order?
Yes.
No. Okay, now we've got 3 coins.
Heads.
Heads, heads. That's not a head, that's a tail.
H-H-T.
Heads, heads, tails.
H-T-T.
H. How about that? Let's move the T. Like, move it.
H.
Or
H double T.
you do whatever you want to do. This is what I'm doing. Okay, then I need H-T-T. T-H-T. T-T-T and T-T-H. Did I get them all?
Yeah.
Okay, the other way I could have done this is, don't I have three things?
No.
Yeah, you do.
Okay, how many possible outcomes for the first coin? And the second?
Two.
And the second?
Two.
So 2 to the third,
Three.
which is?
8.
Okay, we've been doing this stuff, right?
Yeah.
Am I good? Okay, probability. I just talked about this. Probability is, you do not need to write that whole box. You write what you need. P of an event. We will put P of odds, P of hearts, P of. That's how you label your work. What's P stand for? Probability. Okay, this says the number of events. That means the favorable events, which you're looking for, over the number of things in the sample space. Just like we talked in a test, right? The number of points I got right over the total number of points. So the number of things you're looking for divided by the total number of things in the sample space. That's what a probability is. It is a percentage. We can write it as a percent, a decimal, a fraction. I tend to write probabilities a lot as fractions until I get to big, huge numbers. Like 3/4, I'm not going to sit there and 1.75. 3/4. That's the probability. If I have huge numbers, like we just had the 40 choose 12, if that was the total number of possible outcomes on my denominator, and I picked something like 6, well, 6 divided by 5 billion, I wouldn't leave that as a fraction. I would make it a decimal. And 6 out of 5 billion would basically be what?
Too many.
6 divided by 5 billion.
Basically 0.
Basically 0. Is it 0?
No.
No, but it's pretty dang close, correct? So,
1.2 e to the negative 9.
okay, so 1.2, so negative 9. So when your calculator says E, remember that scientific notation, right?
Yeah.
So 0.0000000002. Oh, it's 1.2. Okay, basically 0, yes? But is it 0?
No.
No. Am I good to go?
Yeah.
Callie, good?
Yeah.
Okay, this is why I was pointing this out. A probability of event must lie somewhere in between 0 and 1. This is not a 1.0, guys. That is a period. Okay, so 0 is less than equal to the probability of event, which is less than equal to 1. It is impossible when people say it's 120% chance something is going to happen. That is absolutely impossible. That cannot. Probabilities are, that's not true. Okay, I can get 120% on a test. That's not a probability, is it? No. Okay.
120%, that would be 120%.
Say that again.
Never mind.
Okay. If the probability of the event is 0, if it is 0, it is impossible. If it is 1, it is certain. Is our 6 out of 5 billion impossible?
No.
No, because is there still a chance?
Yeah.
A pretty small one, correct? But there's still a chance. There are very, very, very few things in our world that are 100% going to happen, and very, very, very few that are not going to happen. Like it's impossible to happen.
What would be an example of like 100% chance?
I'm going to die someday. Right?
Yeah. Okay, that's
So, I mean, honestly, everyone in this room at some point is going to die.
No,
We don't know that. We're
Okay.
thinking about
I'm gonna
what
freeze
the-
myself until the late 1800s.
You're gonna
The
freeze
late,
yourself in
the
the
late
Yeah.
1800s.
I don't think she's gonna super insanity, is there?
You're
Have you
right.
seen Captain America?
She is preserved well.
Yeah,
Okay.
I'm gonna be Captain
So-
America one day.
I
I'm not
know.
ready.
Sorry to interrupt, but
Okay.
I called that number the Miami Accessible. It's the Miami Corrections. It's a prison. prison. They gave me the wrong number. And I had to just come tell you because I don't even know where to go with this.
I know where I'm going.
Austin's
Miami?
going there.
The Miami Convention Center.
Austin's going to the
See, I just keep
facility.
You gave me the wrong number.
Maybe we need somebody above our pay grade to.
I guess, but I just
Start
had
raising
to,
it.
I'm sorry, Donna, I
Thank
almost
you.
wanted you to call it yourself, just so you could do that.
Just so I can.
Yeah.
Thank
You're out
you.
of book, you call it your future job.
Okay, so very few things in this. Somebody always says, "Well, I'm going to wake up today, or wake up tomorrow." Do you know you're 100%
Yes.
No.
chance? You'll-
No.
Yes.
Yes.
Did you wake up today?
No.
Yes, but it's not a probability because it already
I
happened.
don't know.
Okay, what's something that is never ever going to happen?
I got a girlfriend.
I'm gonna be born again.
You're gonna what?
Be born again.
You're going to be born again.
I'm gonna
Okay, when we start thinking about things that are never, ever, ever going to happen, we start thinking about things that are impossible, just in general. Can I make an apple and orange?
Yes. If you
I mean, you
can.
can.
No, you can't make an apple and orange.
Because then it'd be an orange.
There's some guy on TikTok who
Yeah.
probably could.
That's true.
Okay, so there are very few things in this world that are the probability of them happening is 0. There are a few things that are 100% yes going to happen. Yes.
People make cakes and shoes. You gotta think about
Oh,
that.
yeah, that's
Like
true.
shoes a cake.
But can you make a?
But can you make
I learned
an
how to do
apple
that,
and
yes.
orange?
Natalie can.
Yeah, you probably could.
If you put in the orange inside of the apple.
Okay. Anyway.
Just put the orange peel around the apple.
Okay, 2 coins are tossed. What is the probability that both are heads? So we need to figure out
1 out of
50%.
what was what was the what was my sample space of 2 coins flipping?
4.
It was what?
4.
4. So my denominator is what?
4.
4. So it's 4 and 4. Yes?
Yes.
Okay. How many heads are on a coin?
One.
1. How many heads are on the other coin? 1. So I have 1/4 times 1/4 because they both have to happen, yes? Is 1 what?
116.
1/16.
You're a smart man, Isaiah.
I was.
How's it?
Wait, I did a wrong problem. I did the wrong problem. I did flipping. I took the probability I did, and I will tell you what I did wrong. I took 1 coin and flipped it, and it wouldn't be one that. I took 1 coin and flipped it. What's the probability of getting heads? What? 1/2. And then I took another coin and flipped it. What's the probability of getting
1/2.
1/2, which is 1/4. But that is not what this question was, and that's not what I did because I mixed the two together. I put 1/4 times 1/4, correct?
Yes.
Okay, so let's do this right. I want 2 heads, yes?
Yeah.
Out of that list of things, how many times could you get 2 heads?
1.
Once. Out of how many?
4.
4. So the probability of 2H, or you could just put HH, is what? 1/4.
25%.
What?
25%.
Yes. So could I have done it this way? Yes? But I also just did it this way, right? Because this way again was with 1 coin. This was with flipping both coins at one time. A card is drawn from a standard deck of playing cards. What is the probability that it is an ace? So how many cards total are there?
52.
So probability of an ace. So there's 52. And how many aces?
4.
And there's 4. So there's 1 13th.
Is that how they're divided?
Yes.
Yeah.
There's 4 suits with 13 in each suit.
Actually,
Yes.
I didn't know that.
Yeah, you do.
I'm glad you learned something, Evan. Okay.
Okay, we good?
Tell all my friends.
Yeah.
He's done. You already told him.
Austin, you good?
Yeah.
Plus the jokers.
Okay. Unless a problem says with jokers, you assume without, because they are not playing cards. They're just extra cards in the deck. If a 6-sided dice is rolled, what is the probability that the total of 2 dice is 7? Okay, so first of all, we're looking for the
The probability of the union of two events?
probability of the sum of 7, right? So when I'm talking about outcomes, the denominator, yes, I would have not 12. I have 6 on one dice and I have 6 on the other, so I have 36. Okay. Now I need the sum of 7.
1 and 6.
I can have 1 and 6. I can have,
2 and 5.
how about 6 and 1 also?
Oh yeah.
And 2 and 5.
5 and 5.
5 and 2.
3 and
3 and 4.
Yes.
So how many ways can I get a sum of 7?
1, 2, 3, 4, 5, 6.
6. So the probability is
1, 6.
now some are easy to do that way, yes.
Yeah.
Okay, some are not that easy. You're going to have to use your combination permutation. Okay, the combination permutation can be both used on the total number of outcomes and on the events you want also. So you could have a choose over a choose or a permutate over a permutate.
Don't make it difficult.
So in Arizona, the pick game, a player chooses 6 different numbers, 1 to 44. If these 6 numbers match the 6 numbers drawn in any order, so what doesn't matter? Order. So we're not permutations, we are what? Combinations if we use it. The player wins the top prize. What is the probability of winning the top prize if the player buys 1 ticket?
Say about 1 out of 2.
So the probability of money. How many winning tickets? 1, right? There's one way to, I'm buying 1 ticket. Now the bottom is, how many numbers do they start with?
44.
But they're picking what? 6, so we need to do,
44 divided by 6.
no, 44, choose 6. Okay? Now, I personally am not going to list all those out. You?
Why?
List the different number of combinations of 1 through 44. No,
I am not going to.
not either. Okay, so I have 1 over 44 factorial over 38, right? 6. Did I subtract right?
I would say so.
Did you say so? Okay. So, when I divide a fraction, I multiply by the reciprocal, yes?
Yeah.
Yes. And there's actually, I can reduce, so it's going to be 6, 5, 4, 3, 2. And the difference between 44 and 38, I'd have 44, 43, 42, 41, 40, 49. 39, yeah, can't count.
I'd say at least 39.
Okay?
Wait, why is the 6 factorial on the top?
Because it's 1 divided by this fraction. So when you divide by a fraction, you multiply by the reciprocal. Is there anything nice we could do to this?
Yeah, use your
45. This could go to 10, right? This could go to 13.
Nothing else.
Well,
Oh, 2 and 42. No. 2
well,
and
6,
44.
6 and 42, right?
Yeah.
That's the calculator.
I mean, 2 could also, but 6 would go closer, right?
2 and 44.
This would go to 2. 2 and 44 would be 22.
Yeah.
So I have 1 over 22 times 43 times 14 times 13. Where'd the 14 come from? Where'd the 14 come from? 7 times 2. So let's see what the probability of us winning this thing is.
I'd say that's
It's
at least, if I just had to guess.
When you
Yeah,
put this in your
72,000.
calculator, you need to put parentheses around your denominator.
Did you miss the
You
41 or
forgot.
where did that one go?
Oh,
Oh, if I had to guess, it'd be about 7,059,052.
no, I didn't ask what that number. I asked what the probability of me winning.
Okay.
So-
7,059,052.
It is approximately 0.000013.
What's that last number on the end there, around 13?
It's a 1. 41. It's just so close and messed up. So that is the probability of us winning the lottery.
Yay.
Let's do it.
What if we all just buy all the tickets?
Okay, so the possible number of tickets, which Kale was telling you, is 44 choose 6, yes?
Yeah, that's
So 44 choose 6
Yeah, it's a 41.
is 7,
7 million.
yep, 7,059,000.
14.
7 times 2.
Oh, okay.
52. So that's the total number of tickets that you would have to buy every single ticket.
Much money then.
Yes.
That's that many dollars. If it's $1 a ticket, or if it's $2 a ticket, then you have to double that.
But we have Taylor.
Yeah.
We do have Taylor.
This is why
We
we
have
got
Taylor.
We have Taylor.
And
3.
Okay.
And Natalie.
Yeah.
My
Yeah, you
calculator
usually
did
forget about
something wrong.
Natalie.
And
Brad.
13.
yeah, but she's not
I
here.
got 1.4.
Yep.
That is not right.
Taylor.
Let's make my calculator.
Fine.
did
When
something
that with 6 zeros in front of it, it really doesn't matter. It's 1 point.
You're gonna be like, how-
Yeah, mine's 17.
wrong. How did I get a
Mine is
calculator?
Mine's 7. No, it's not 7 zeros. It's 1 point. So you have to move it 7 places back. So it'd be 6 zeros and then the 1. What?
I got 14,000. 14,000.
It does it say e to the -7?
It doesn't say anything.
Okay, then something you just put it in there. I don't know.
It's coming back in a couple of days. It's like 10, 12.
Okay, so let's move on. You guys are not staying on task at all. Okay. 2 events, 2 things happening. Okay? If A and B are events in the same sample space, the probability of A or B. So far we've been dealing with ands, correct? Yes? This is an or situation. Okay? If I want A or B. So what we have to do is find the probability of A, find the probability of B, and subtract their intersection. Okay? That's what the upside down U is. There's their intersection. So what that means, if I want the probability of girls or juniors. Do we have girl juniors in here?
Yeah.
Yes. We can't count them twice, can we?
Yes.
No. So that's why you can count them, but then you take out what they share. Okay, and I'll show you a picture in a second. Unless you have A and B are mutually exclusive. Mutually exclusive means they have no outcomes in common. Okay? If I want a junior or senior, do I have any of those outcomes in common? No. I said junior or senior. You can't be a junior and a senior at the same time, can you?
Unless it's in the
I
summer.
feel like Brad could find
Okay? No, you cannot. You are a junior or a senior.
I'm going back next year.
Okay? So, there, yes, ma'am.
What's that UE? What's that symbol? The upside down U.
The upset is intersection. The U up is union, means the total thing. The U down is intersection, means where they touch, and I'll show you a picture in a second. Okay? Probability of A union B. That's actually not union, sorry. It's the probability of A or B. Sorry, I shouldn't say union. And then the upside down is the intersection of the two. So if you think of a Venn diagram,
Yeah.
you know what a Venn diagram is, yes?
Yeah.
Yeah.
This is the intersection.
Yeah.
So things I have in common.
Yep, whatever would be in both. Because you can count all of this and you can count all of this, but you can't count this stuff in twice, can you?
No, ma'am.
And if it's mutually exclusive, when I draw this picture, there's stuff here and there's stuff here, and there's nothing in the middle.
Then why'd you draw them overlapping?
Because that's how a Venn diagram works.
But not if there's
Just
no
done.
middle, then you wouldn't draw a Venn diagram.
Draw two circles.
You could draw it like this, you could, but you can also draw it like this.
All right.
Okay, am I good?
No.
Ands we multiplied, ors we do what? Add. And you multiply, ors you add. When you're reading the problem, if it's this and this has to happen, you multiply your outcomes.
What's the
Okay.
upside down union do?
Intersection.
Oh.
Like fifth or sixth time now.
I like the third.
No, because that's what I was explaining the whole time.
No, read a list. That is
Okay,
the third time.
so,
Just say
and we do what?
Multiply.
Or we do what? Add. I will tell you that a lot of times you take care of the subtraction when you're adding it up. You'll be like, oh, this is the number of whatever, and then this is the number, oh, but we got to count in some of them, so we take it out. So sometimes you take it out as you work, but that's actually what's happening. Okay, so here's a picture. One card is selected from a standard deck of 52 cards. What is the probability that the card will be either, which is an or, right? Heart or a face card. Okay, so how many hearts are in the deck?
13.
Okay, just a second. Probability of a heart or face card. Yep. So there's 13 out of 52 hearts. Yes?
Yeah.
How many face cards are there?
12.
12. 12 face cards out of how many cards?
52.
52. But how many of them are hearts and face cards?
I'd say about
3. And if you don't reduce, which I would highly suggest not doing, do they all have common denominators already? Okay, so 13 minus 3 is 10. 10 plus 12 is 22 over 52. So 11 over 27?
Nope.
That is not right. How about 6? Right?
Yeah.
Yeah. Yep.
Does that make a clearer picture of that?
Yes, it does.
Questions? Am I good to go? I forgot what percentage of the questions on the ACT are probability ones.
It's like 28.
No.
It's about.
Okay.
Like,
That was
I'm
a lot.
talking about like number of questions, like 2 or 3, but they're basic. Okay, a personnel department of a company has compiled data on the number of employees who have been with the company for various periods of time. The results are shown. If an employee is chosen at random, what is the probability that the employee has 4 or fewer years of service?
Add them up.
You gotta add them all up, don't you? Why do we have to add these all up?
Because those are all the
Yeah, those are all my employees. That's my denominator, isn't it?
The big number is 492.
492. Anybody agree with that?
I got 592.
I got 592.
What did I do wrong?
Got 529.
The book got 529.
Okay, I got 529. That's what I got. My calculator says
Oh, I forgot
529. I just
37.
stayed quiet.
I read it 592.
Okay, so
I just forgot 37.
well, that probably makes a difference.
No.
Okay, so
I don't see the
529 is the total number of plays. So 4 or fewer plays. How many is that? How many is that?
457.
P of less than 4. Yes? See how you write those? You kind of just say what you're doing. Okay, so it was 592 or 529. You guys got me saying numbers backwards.
No, you said numbers back.
Add over that. How many?
157.
157. Now, this is the answer I want reduced. You guys are all going for your calculators. I didn't ask you for a decimal, did I?
Well, you did it earlier, and you're just like, nope, percentage. So.
Okay, I did it because it was 0.000003.
Okay.
That doesn't make much sense to us. Can I reduce these numbers? 12, 13. Not unless 7 goes into it. 7 doesn't. 3 doesn't. If 3 doesn't, 9 doesn't. I guess 17, but nope. Okay. So what is the probability or 9 or fewer years of service?
Wherever 157 plus 89 is.
Yeah, that
So what you're doing is 157. What you're actually doing is 157 over 529 plus 89 over 529, correct?
yeah.
So what you're actually doing, but at all intents and purposes, you're going to add those two together. You've done that for years, right? Why don't I have to subtract anything on here like I did the cards?
Mutually exclusive.
Because they're mutually exclusive. So 6, 4, 2,
Yeah.
46.
Yeah.
Now, if you guys put 246 divided by 529 in your calculators right now, everybody do it. Don't hit enter. Just type 246 divided by 529. Do not hit enter.
Wait, how do you know if they're mutually? What?
They have nothing in common. Like I'm 4 or fewer, or I'm 9 or fewer, like 5 to 9. There's no overlap. This is 0 to 4 years, and this is 5 to 9 years. There's no overlap. Okay, everyone has
Yeah.
426?
Yeah.
Go to math. Math is an amazing button. The very first thing you see at the top is what?
Math.
It's fraction. If you hit enter now, and then hit enter, it will reduce the fraction if it can. It cannot. But do you see that? It reduced the fraction for you. So when you have those larger numbers, throw them in there to see if you can reduce them.
Thank you, Miss May.
You're welcome. Okay, questions on this one?
You can't reduce 137.
Right.
529.
Good job.
Okay. Okay.
Got embedded.
When you click on the math thing,
At least.
Okay.
There is at least one. I'll give Isaiah that. I hate to do it.
I don't know if you do, because then we just have a bunch of questions tomorrow, so I'd rather do a bunch with us. Okay, independent events. What we have been doing is independent events. When we did the license plate, yes?
Yeah.
You had letters and numbers. Picking the first letter had no dependence on picking the second number, did it? Okay, when it's an and situation, what do we do? Multiply. When it's and, you multiply. I hope that's basically all you're writing. Okay, they're independent events or two events that have no effect on each other. And when it's and, we do what?
Multiply.
Multiply. This is what you need. You don't need all the other. It just says if they're two independent events. If one affects another, you do it differently. So when you are reading these problems, you need to know whether they are independent or dependent. You need to know if order matters. If it doesn't, do you need to read carefully?
Yes.
Yes?
Seems easy enough.
Okay, are we good? So we could do one?
Yeah.
Okay, a random number is generated on a computer, and a computer selects three integers, 1 through 20. What is the probability that all three numbers are less or equal to 5? So I want the probability of less than equal to what? 5. Okay, so 1 through 20, how many numbers are there to choose from? 20. Okay, and then I'm going to do it again. Yes? And a, again, and a, and a.
You only said 3.
It does only say.
Oh, 3 times. I don't know where I was getting 5. Oh, the 5
You just.
equal to 5. Okay, so how many numbers are less than equal to 5?
5.
5. And?
5.
And?
5.
So 1/4.
1/4, and I'd say about 1/4.
So 4 cubed is?
64.
Okay. So read carefully.